But really, today I want to talk about something that is really not, I think, not very well known amongst a lot of people, even not just in the streaming community, but in the vector database and the generative AI community as well. And that's actually how we use Kafka within Milvus to enable scalable similarity search and scalable vector search overall. So this is a really interesting topic, a really exciting topic, and I hope it's something that really lies at the intersection of Gen AI, of vector search, and also of streaming as well, something that'll be of interest to everybody here. So again, that's a picture of me when I was a little bit younger and fewer wrinkles and white hairs than I have right now. But I'm Frank, head of AI and ML here at Zilliz. Feel free to connect with me. I'll have some QR codes at the very end as well, but that link to all of these. But that's my LinkedIn, that's my Twitter. Go ahead and connect with me if you have any follow-up questions or if you want to ask anything later on. And a quick introduction to Zilliz as a company. We are the key maintainer of the open source vector database called Milvus, which is what this particular talk is going to be about. And going beyond that, we were actually founded in 2017, and we actually started working on vector databases, vector search in 2018. So we've been doing this for a really long time. Way before you saw a lot of the interest, hype, as some people would call it, around ChatGPT, around generative AI, and many of these other models that we see today as well. So I'm going to talk about three things primarily, and the first is I want to just give a recap into vector search and vector databases more broadly, right? Why do we care about them? Why are they important for your application? What can we use vector databases for beyond generative AI and beyond using them in conjunction with LLMs? And then I'm going to talk a bit more of a deep dive into Milvus. And this particular deep dive, I'll try to focus a little bit more on how Kafka almost forms a bit of a backbone for a lot of the work that we do. A lot of the work that Milvus does internally. And then I'm going to give a sneak peek into what I believe the future of vector databases and the future of vector search looks like a little bit more broadly. So without ado, let's just dive right in. Some of you might know this. I think some of you might have seen some of these slides from maybe if you've seen an earlier talk that I've done or something along those lines. But the idea is that there's so much unstructured data out there. And we have this diagram in many different forms, but this is one that I like to use just for more infrastructure, more tech talks. And yet we have tons and tons of unstructured data out there. They come in a variety of different forms: text, images, video, audio, but there's many more examples of that as well. Molecular structures or 3D models, right? Or let's say, housing footprints, stuff like that. These are all great examples of unstructured data, and these are examples of pieces of data that you really can't store inside of a traditional database, inside of, let's say, a NoSQL database or a relational database or a wide column store. So how do we store, index, and search these different types of unstructured data, especially with there being so much out there now? And really the key is to use embedding models, or usually, well, right there, it says up there deep learning models, but usually they're neural networks that take that input data, train neural networks, that take that different modalities of input data. Again, it could be images, video, audio, text, or many other modalities as well. And they turn them into an embedding, turn them into a vector. And that vector is usually a great representation of the input data. That vector is a representation of what makes the semantics. It captures the semantic properties of that input. So for example, if I had two images and they were very, very similar to each other, or if I had a piece of text that described an image very well, and I vectorized both of them, those two vectors would be very, very close to each other in this high-dimensional space. So this is the property that vector databases leverage to give you really, really powerful unstructured data search and unstructured data analysis. And one of the things that I really like to say is that vectors or embeddings, I like to use the terms interchangeably here, vectors are the language or the phrases, the words that machines use to describe unstructured data. That's what they use to describe images. That's what they use to describe audio snippets or IMU data. Now this particular image, or this particular diagram that you see here is from a 2023 meta paper called ImageBind. And ImageBind, essentially what they're doing, I'm not going to dive too deep into this, but for folks who are a little bit more familiar with embedding models and who are a little bit more familiar with how neural networks work, ImageBind is essentially a 6-modality model. It uses images and other visual data as a central modality, and it binds 5 other modalities. So what you're able to do is, if we just focus on that first row of cross-modal retrieval, you're able to take audio that corresponds to a crackle of a fire, and if I retrieve the most relevant results in my vector database, if I retrieve the most relevant visual data, or I can retrieve the most relevant text, right? I retrieve the most relevant results in my vector database, and it describes that input very, very well, or it is correlated with that input very, very strongly. And again, as I mentioned in the previous slide, this is the property that vector databases use, well, to really give you large-scale unstructured data understanding and unstructured data search. This is one of my favorite ML models today. I'm sure that'll change in the future, but this is where, just to give you a heads up of how you can think about vector search and how you can think about vector databases a little more broadly. So I think the killer application for all this is very, very clear. So how many folks here are familiar with RAG? I know we don't have a ton of folks in the audience today, but anybody familiar? Quick, oh, okay, there we go. We got one in the back. All right, very nice. So the killer, this is from the LangChain blog. The killer application is retrieval augmented generation. A lot of people use vector search and vector databases for that today, right? The key idea is that we have, let's say, we have a large language model, and we have a question, we have a prompt that we want to pass in. But beyond that as well, we also need to add extra context. We also need to add extra information. That information comes from our vector store, from our vector database. So what we'll do is we'll vectorize that prompt, search for the most relevant documents or other pieces of data inside of our vector store, inside of Milvus, inside of Zilliz, and then pass that along with the prompt to our large language model. And that's going to give us a much more reliable answer than what we typically have. All right, so this is retrieval augmented generation. It's a commonly used paradigm with large language models today. And this is the most common application for a lot of vector databases. But really, things go way beyond that. It goes way beyond RAG. It goes way beyond using vector DBs in conjunction with LLMs. I'll just give you a couple examples up here. Image similarity search or multimodal search, right? You have AI-powered drug discovery. Or if you can vectorize graphs, you can vectorize vertices and nodes in a graph. And if it's a supply chain, you can understand what are the redundancies in a supply chain. These are all things that you can do with a vector database if you have the right vectorization strategy, if you have the right way of turning that unstructured data into vectors, okay? All right. So we went over why you need vector search. We went over why you should care about vector databases, right? What makes them really, really unique in this world of so many databases out there? Relational databases, MongoDB and key value stores and wide column stores. What makes vector databases unique is that they store, index, and search unstructured data. Talked a little bit about Milvus a little bit earlier already as well. Milvus is an open source vector database. It's created at Zilliz. It's got something like 30,000 stars on GitHub now. I know it's a bit of a vanity metric, but I think in part it shows you just the sheer amount of interest there is in vector search today, and also the size of the Milvus community as well. So what makes, now I'm going to talk a little bit more about infrastructure, data infrastructure in particular. I'm going to put my data infrastructure hat on. What makes Milvus different from other vector databases? I think you can distill it down to two key things. The first is scale, and the second is performance. So how do we achieve better scale and better performance? Well, it's a distributed system. Okay, so unlike a lot of other, some other popular vector databases too, I'm not going to name any names, which are not distributed systems. They don't scale very well, and they definitely don't scale horizontally. We do. And eventually I'll show a picture of the Milvus architecture, which will serve as a good backbone for why we scale so well. Second thing is that we are real time, right? We are not simply a batch database or a batch processing system that you see. You can't replicate what we do in, let's say, a series of Spark jobs. The third thing is that we have very, very data-driven optimization. We combine a lot of strategies for indexing metadata along with the vectors, and we have our own unique way of indexing vectors inside of the vector DB as well. So what does that give us, right? That gives us really, really solid performance and much better than what you typically get in other vector databases. I talked about real-time read and write just one bullet point ago, but that doesn't mean that we don't support these batch processes as well. We do. It just means that when you want to do a backfill, when you want to load your vector database with all the unstructured data that you have right now, all the vectors that you have, You can use bulk insert, you can use bulk import, and get all that data there before you turn your application on and start ingesting data in real time. All right, so Milvus 1.0 to 2.0. Milvus 1.0, I'm going to take one step back to the previous slide here first. Milvus today is a distributed system, and it's a very, very scalable and high-performance vector database. But that wasn't always the case. The first version of Milvus, which was released, I want to say open sourced in 2019, we started working on it in 2018, and it was open sourced in 2019. The first version of Milvus was a single instance. Everything just resides on a single machine. And if you want to scale it, you really got to scale it vertically. Similar to maybe some of the older versions of MySQL and some of the older databases, relational databases that you see today. You can only scale it vertically. So everything, all the components, the individual components that you see in the vector database, those are all just on one machine or on one pod or on a single node. So that includes the proxy. I apologize for the spelling error up there. That includes the proxy layer, right? So what interfaces with the SDKs. It includes a storage layer, right? What interfaces with object store, and then the indexing and the querying as well. All that resides on a single machine. So you can imagine how this presents some problems. If I am ingesting a lot of data, all of a sudden my query speed reduces simply because I'm using a lot of the CPU cycles on that machine to do indexing. If I'm doing a lot of querying, well, I can't ingest that much data anymore because, well, for exactly the opposite. Now all of a sudden, I have a lot of client requests coming in, and then the indexing is going to have to slow down as a result. So it's a very, very brittle system, and something that's not really ideal. So the evolution to 2.0, the first obvious thing that you do is you split all of these individual ones out, and you make all of them individual clusters. So we make the proxies are now stateless proxies, and they reside. They reside outside of the single node. You can have a number of different pods for them. The data nodes are for data ingestion. Query nodes are for querying, and the index nodes are for when you have a lot of vectors that have been ingested for building the index across all of those vectors. So now we've split out all of these individual tasks to their separate pods in a distributed system. But we've got to tie it all together as well. We've got to tie it all together. And when I go through the read path and the write path, hopefully it'll become a little bit clearer as to why we need to do that. But let's talk about how we use Kafka, and in particular, how we use other streaming technologies in Milvus 2.0 first. Really, it almost forms the backbone of everything. Right? So for example, when I have a search request, that's OK. Doesn't really need to go through any of these other components. It just comes into the proxy, and then it goes directly to the query cluster, and the query cluster will return the relevant it'll return the relevant searches. It'll return the nearest neighbors to my input vector, to my query vector, and you'll get that back directly through an SDK. But now when we want to insert data, right? When we want to insert data, it's a more complex process. So the insertion workflow, it'll actually first go to the write-head log. It'll first go to the log sequence. And we use Kafka because, first of all, it's distributed, and it gives us the capability, because each of these individual pods in the cluster can, they can read from all these individual topics, and they can read from different channels that correspond to collections and partitions within the Milvus cluster. Now, all of a sudden, we can make things much, much more flexible. So let's look at the insertion workflow here as well. Now we have a vector that we want to insert into the vector database. It first goes to the write-head log, to the write sequence. And then the data nodes will ingest those vectors. Those vectors, the data nodes are really only responsible for ingestion, for taking the vectors, turning them into individual segments, and then writing those segments into S3. So that's what the data nodes are responsible for. That's pretty easy. Once those segments are sealed, you actually they get sent to the index nodes, and the index nodes will be responsible for building the index across them. Now, once that index is done, it gets written back to S3, and the query nodes will load up these indexes, and then they can start querying directly from them as well. Now, before that index gets built, we also need the query nodes to have the vectors that were most recently inserted. This is a very important point. And this is why Kafka is so helpful. This is why we need some sort of streaming technology inside of the vector database in order to make things much smoother, in order to make things, well, in order for individual pods to be able to subscribe to the topics that they need to subscribe to in order to get the data that they need to, right? So the query nodes also need to subscribe to the log sequence simply because we need to make it a real-time database. We need to have those vectors that are freshly inserted to be able to have them immediately queryable inside of the query nodes. So we put it all together, you can really see how the log sequence, how Kafka really sits at the center of all of this, putting everything together and making everything, well, quite frankly, really awesome and distributed. So what are the key takeaways from this kind of architecture, right? What are the key takeaways, and how does this make us better than other vector databases? How does this give us the capability to target so many different applications? Well, first, we separate storage and compute, okay? You'll see that data and index and all of the other pods that are running the computation, well, they're fully separated. So not only do we have good separation of storage and compute, but we also have separation of different types of compute as well. So the data nodes, the query nodes, and index nodes, they all can do their own separate jobs. Now, all of a sudden, if we have, let's say, an application that has very, very high write throughput, but maybe doesn't query that often, we can reduce the size of the query nodes, or we can reduce the size of the query cluster, and we can add data nodes, add index nodes, and that'll give us up-to-date indexes and up-to-date segments, well, pretty much at all times. If we have the reverse, now we can reduce the size of the data node cluster, reduce the size of the index node cluster, potentially even just have a single pod that functions as data nodes, and then increase the size of the query node cluster. And what that'll give us is the capability to just do lots of queries, and if we need to add more replicas, we can do that as well to really double or triple or quadruple the throughput that we need in our vector database. And all of that is made possible by having Kafka be our distributed write-ahead log inside of the database. Okay? So again, separation of storage and compute, what does that give us? It gives us good scalability, gives us good isolation, and we have the capability to do pooling too. So you can imagine now we have an index node, and that index node, we can take all of that out, and that can form an index pool. And to really tie everything together, to really make everything a little bit clearer, we have these concepts of data structures inside of Milvus as well. I talked about this a little bit earlier, but each set of vectors inside of Milvus is called a segment, and those segments can become sealed, and then once those segments are sealed, indexes are built across them. And then if you have growing segments as well, those segments are also available inside of the query nodes, and those will be queried in what is essentially real time. One last thing that I want to go over, this doesn't relate too much to how Kafka makes a huge impact in Milvus, but one last thing that I want to talk about is compaction. And if you have, let's say, if you do a lot of deletes in your vector database, what ends up happening is that we first do a soft delete. So rather than removing the vector from a sealed segment altogether, we will simply flip a bit, and we will say, okay, this vector has been deleted. Do not search across it anymore. But once you have, once let's say 80 or 90% of the vectors in the segment have been deleted, you end up getting poor performance simply because now you're traversing all those segments, you're traversing all those vectors, and you're not actually, only 10 or 20% of them can be used. So that's why we undergo a process called compaction as well. And what compaction does is it takes multiple segments that have had a high percentage of deletes and combines them into a single segment. I think I might have a diagram that sort of shows how it happens here. Yeah, so you have some segments here, and they become one larger one, and the same thing here. All right, so let's put it all together, okay? Let's put it all together. So if we had, this is the full Milvus architecture, and really what happens here is not only do we have that separation of storage and compute, we have separation of different types of compute, but now we have everything in here is distributed. Everything in here, we can add a lot of redundancy into the network as well. We use the message store, we use the log broker really as the backbone, as the spine of the entire architecture. And that is what gives us the capability to really not just be a distributed database, but also to target all those different types of applications that we want to be able to target. High read throughput, high write throughput, batch, stream, so on and so forth. It gives us capability to go through all of those. One last thing that I want to mention is that not only do we use Kafka inside of our vector database, inside of Milvus, but we also give you the option to use it outside of our vector database as well. So we have what is called the Milvus sync connector for Kafka and for Confluent. That is available, well, it's available today, and you're free to use it in whatever applications that you guys are building. But really, at the end of the day, it forms a really, really important part, I believe, of the broader vector database ecosystem. So I think today, sure, we use it inside of our vector DB, but also there will be many, many use cases out there for streaming real-time data, vectorizing that data, and getting that data stored, or potentially querying a vector database with that data. All right, and for the last maybe 7 or 8 minutes or so before I open up to questions, I want to talk about the future of vector databases, sort of like a sneak peek as to what I believe vector DBs are going towards. I realize I think I missed a slide here, but there are many, many ways that you can use vector DBs. I touched upon some of this a little bit earlier, but two of the examples you can actually already see here. The first is with molecules to do AI-powered drug discovery. Right? By really encoding the functional groups and encoding the individual bonds inside of a molecule, you can actually turn a molecule into a vector, and that vector will simply be very, very representative of what that molecule is capable of doing. So we actually already have a lot of folks that use both Milvus as well as Zilliz Cloud, our managed service, to build this kind of application. I think the second, let me see if I'm missing a slide here. Oops. Okay, so the one in the lower left-hand corner, pretend you haven't seen that yet. The second one that I want to talk about is audio. You can vectorize audio as well, speech in particular. And what that really gives you the capability, this right here is called wave-to-vec 2.0. What that gives you the capability of doing is now you can search for, let's say, if I have text, and I want to search across, let's say, a lecture. Now I want to find the corresponding lecture snippet that answers, let's say, my question if I'm a student, right? Now all of a sudden I can do that because I can encode audio. I can turn audio into a vector. I can store that vector inside my vector database, and I can search for the most relevant audio snippet given some input data. I can do the same thing for graphs. I'm not going to go over this too much, but by encoding those individual, encoding all those connections in a graph and putting them into vector format, now all of a sudden I open up a broad range of different applications. Things like anomaly detection, or I can do things like understanding if there are different cycles or if there's redundancies in my supply chain. A lot of these are great examples of how you can use graphs inside of a vector database, or vertex embeddings, node embeddings inside of a vector database. And last but not least, time series data. Now, this is time to vec. You see a lot of these vectorization algorithms are called X to vector. Not very creative, but I think it shows you exactly what the capabilities are. And for time to vec, by having different hierarchies of time data and contrasting all of those together using, training all those together using contrastive learning, all of a sudden you get a really, really powerful self or semi-supervised version of vectors for time series data. Great for things like forecasting, great for things like potentially classifying individual time series. If you want to understand, hey, what periods correspond to a recession, what periods correspond to great periods of growth, this is one of the ways that you could do it. Right? There's many, many more examples of data that can be vectorized beyond these four modalities. And this is just to give you, I think, a sneak peek as to what vector databases are going to be good for and what they're going to look like in 3 to 5 years, if not 1 to 2. They're going to be used for way, way more than just retrieval augmented generation. They're going to be used for way more than just recommendation. We're going to start using them for really as general purpose unstructured data stores. And there's many, many applications out there. The possibilities are endless. And at least for Milvus, as the log broker, as that core backbone, Kafka really makes it all possible. So one last thing that I want to say, one last thing that I want to leave off with is the question of, are we done, right? It sounds like we're done. We've solved all the problems out there, okay? We have all these great embedding models, and I talked about, here how there's endless possibilities for ways that we can vectorize data. We have all these great embedding models. Now Milvus is a distributed system, and you can do approximate neighbor search in it. You have data nodes, index nodes, query nodes. You have the coordinator layer. Kafka really helps tie all of it together. So it sounds like we're done, right? And I think the answer is definitely not. We are not done. And the reason is simply because this space, machine learning and artificial intelligence and generative AI, if you like to use that term, it's growing very, very quickly. Beyond that as well, many of these applications will involve things that go beyond approximate neighbor search, that go beyond vector search. Maybe we want to do things like regression analysis, or maybe we want to do things like clustering. We want to identify clusters of our input vector data that are really similar to each other, that really makes sense. And there's many, many different ways that vectors are going to be used in the future as well. Maybe we have some sort of multimodal fusion where we want to do a lot of different types of cross-modal retrieval, right? All of that are things that the ML space is growing into that we need Milvus to be capable of handling as well. So a quick sneak peek as to what some of the things that we're working on are and how they relate to the broader AI and ML space. So we have what I like to call hierarchical search indexes. So vector indexes that combine the properties of many current vector indexes into one that gives you really, really solid performance over many different types of queries, many different types of top K, or if you're using range search. We also have potentially the capability, I'm not saying this is definitely coming, but potentially the capability to automatically detect and cluster what is in the database. This is something that is not available in any of the other dozens of vector databases out there today. And then we have indexes over metadata as well. And by metadata, I simply mean data that you attach to each vector that is associated with it. Simply, it could be something like a user ID, or it could be some sort of geolocation. It gives you more information about what that vector is associated with, or maybe where that vector comes from. Okay? And we'll have indexes over metadata as well. So next time you hear a pitch from, let's say, like MongoDB. Okay, next time you hear a pitch from MongoDB and they say, hey, you should use us because we support NoSQL data, we support document data, we support objects in addition to vectors. You should ignore all those purpose-built vector databases. I think you can always retort back by saying, vector databases also support JSON data. It's simply not what we're focused on. Right? If you're an AI native company, or if you're building an AI native application, you should always, always, always use a purpose-built vector database. So with that, I just want to say you can go ahead, start building your application today. Milvus is 100% free and open source. This is wrong. I apologize. There's a typo here. It should be pip install PyMilvus, PyMilvus. So if you're using Python, if you're developing in the generative AI space, that is our embedded version, so to speak. We also have what's called Milvus Standalone. And Milvus Standalone, you can install that just via Docker. You can grab that on milvus.io. And then we also have Milvus Cluster, which is the big granddaddy of them all. That is the architecture that I showed several slides back. And all of these are available for you to go from to help from your journey to just, let's say, building out a small application to something that you need to store 1 billion vectors and get 1,000 QPS on. Right? And if you want to, I also put some QR codes up here if you guys are interested. If you want to know a little bit more about Zilliz Cloud, or if you want to use the Confluent connector as well, these are up here today. I'm going to leave them up there for maybe about 10 seconds if anybody wants to take a quick picture of them, or to go to the QR codes directly as well. And then if you want to connect with me, I promise to give some QR codes at the end of the presentation, so feel free. That's my Twitter on the right, my LinkedIn on the left. I'm a little bit more active on LinkedIn these days. I don't really post a whole lot to Twitter, but if that's your thing, feel free to connect with me there as well. I'm going to leave this up there for probably about another 10 seconds before I end the talk and hand it over to the audience for any questions that you guys might have. Thank you.